On here. So now we're going to be talking about adding and subtracting. So kind of to get us back on track, so back to Pete's Jeep tours, okay? So after we found that Pete collected $150 from each passenger, we ended up with a new chart because we have a new random variable, the amount of money Pete collects on a randomly selected day. We also found that I was going to have obviously a new mean and standard deviation. All I had to do was just multiply my previous mean and standard deviation because multiplication by a constant just multiplies each of your values. Okay. Now let's twist it and say that it cost Pete $100 per trip to buy permits, gas, and ferry pass, The random variable now is going to be V, and it's going to describe the profit that Pete makes on a randomly selected day. So the profit's going to come from subtracting out his expenses, right? So instead of having 300, 400, 450, right, it changes a little bit. So now we have the profit is going to be 200, then 350, then 500, then 650, then 6 passengers would be 800. Probability distribution, though, again, wouldn't change. Okay, so now we have to take a look at what it does to our shape. Well, our shape doesn't change, okay? Our shape is still the same, so our shape never changes regardless of if we multiply, divide, add, or subtract. Shape always stays the same. But your mean and your standard deviation are going to change, okay? So it's fairly clear from the example that subtracting if we go through it again, right, and we do finding the mean, right, so we have, or the expected value, so we have 200 times 0.15 times 3 plus 350 times 0.25 plus 500 times 0.35, and go through the whole thing all over again, you would end up with with a mean of 462.50, okay? Your standard deviation, however, as you go through the whole thing, it will not change, okay? So your standard deviation, regardless of subtracting or adding, it's going to stay. It does not change. So you can go ahead and do it. So 200 minus your 462.50 squared times your 0.15, add it to each one of the next, and you will end up with 163.50. It does not change. So when you add A or subtract A from measures of center and location, but it does not change the shape and it does not change the measure of the spread. Okay, so whether we are dealing with data or random variables, the effects of linear transformations are the same. So this is just kind of like an overall glimpse of what we've done, right? The probability distribution of y has the same shape as the probability distribution of x, okay? The mean is going to add and multiply by your original mean. Your standard deviation would only be affected by multiplication or, of course, division, okay? It is not affected by adding a constant. So let's take a look at this example. Be done with this video. Okay, so one brand of bathtub comes, so the baby in the bath water, okay? One brand of bathtub comes with a dial to set the temperature, the water temperature. When the baby safe setting is selected and the tub is filled, the temperature of X of the water follows a normal distribution with a mean of 34 degrees Celsius and a standard deviation of 2 degrees Celsius. So we have a mean of 34 and a standard deviation of 2. Okay. So if we're going to define a random variable y to be the water temperature in degrees Fahrenheit when the dial is set on baby safe. Okay. So we're going to find, first, we're going to find the mean and standard deviation of y, okay? So the mean is going to be affected both, right? So y is going to, I need this to change to Fahrenheit, right? So the mean is going to be affected by both adding that 32 and multiplying by that 9/5, right? So 9/5 of the original mean plus the 32. Okay, so that's 9/5 of the 34 plus 32 is going to give you 93.2 degrees Fahrenheit. Your standard deviation is only going to be affected by the multiplying by the 9/5. Okay, it will not be affected by adding that 32 to Fahrenheit. Okay, so 9/5 of the 2 is going to give you 3.6 degrees Fahrenheit. Okay, so now kind of like a follow-up question that we could do. According to Babies R Us, the temperature of a baby's bath water should be between 90 and 100 degrees Fahrenheit. Find the probability that the water temperature on a randomly selected day when the baby safe setting is used meets the Babies R Us recommendation. Show your work. Okay, so it's obviously continuous because it's a temperature. We know it follows a normal distribution, so we'll use a normal curve. Okay, so we're going to find the normal distribution of 93.2 of a mean, because that's in Fahrenheit, not Celsius, because they refer to it, the safe being in Fahrenheit, and a standard deviation of 3.6. So I'm looking for the probability of the water temperature being between 90, using y, not x, 90 and 100. Okay, so that's where I'm going to do norm CDF. Okay, of 90, that's my low bound, 100 is my upper bound, 93.2 is my mean, 3.6 my standard deviation. It gives me 0.7835. Okay, so there is about a 78% chance that the temperature of the water meets the recommended temperature on a randomly selected day. Okay.